Is this working? Excellent, thank you. Perfect. All right. Sorry about that, not sure what happened. Let's give it a minute. It's a bit slow. Well, so let's say this. If it stops for whatever reason, I'll switch to Zoom. And I'll send an email with the Zoom link. Very good. All right. So last time we introduced the idea of critical points in a way that was very similar to Cal 1, right? In Cal 1, critical points were points where the derivative is 0 or the derivative does not exist. Here, in higher dimensions, critical points are where the gradient is 0 or where the gradient does not exist. And as you know, the gradient incorporates all the partial derivatives. So you need all the partial derivatives to be 0, or at least one of the partial derivatives not to exist. And our goal, well, we saw that local max and min can only occur at critical points. Very laggy, we'll see. I mean, maybe it'll kick us out and we'll switch to, is it laggy for a lot of people? All right. Very good. So our goal for today is to classify these critical points. So if you have a critical point, is it a local max? Is it a local min? What's going on there? In Cal 1, we had this first derivative chart, which could help us, which could help us classify critical points. However, we don't have that in higher dimensions. What we do have is an analog of the second derivative test. So let me state that. More complicated. If you remember the second derivative in Cal 1, the second derivative test, if you had a critical point where the derivative was 0, if the second derivative was less than 0, it was a local max. If the second derivative was greater than 0, it was a local min. Here, a bit different. Let the second partial derivatives of f of x be continuous. On a disk centered at AB, where the gradient of f at AB is 0. Let D and let d be this. Right? By having the second partial derivatives be continuous on a disk, by Clairaut's theorem, you have, thank you, absolutely, fxy here. By having the second partial derivatives continuous on a disk centered at AB, you know that f of xy is the same as f of yx. Right? So let's define D as this, which really incorporates all the second derivatives. Right? If D is bigger than 0 and fxx is bigger than 0, then f has a local min. At AB. If D is bigger than 0 and fxx is less than 0, then f has a local max. And if D is less than 0, f has a saddle point. At AB. D is a disk. No. D is not a disk. D is this number. I thought you were referring to this disk here. No, D is just a number. It's really D as in determinant, right? This can be viewed as the determinant of a 2x2 matrix. Exactly, the Hessian Matrix. And this is how this is how the second derivative test extends to higher dimensions. I'm not going to discuss it in higher dimensions. Perhaps that would be a good topic for Professor Humphreys to discuss in the workshops. But yeah, as far as we're concerned, this is going to be good enough. What is a saddle point? And that's an excellent question. What is a saddle point? Well, let's consider an example where you have a saddle point, and we'll discuss the graph of that function, and you'll see what happens. So, example, if you take a function, what function do I want to take? X squared minus y squared. What if D is 0? If D is 0, the test is inconclusive. So consider this. First, let's find the gradient of f, which you know to be 2x minus 2y. And so this gradient exists everywhere. The gradient is, so the only critical point is the origin, right? This is the only place where this is equal to 0. Let's classify the origin using the second derivative test. fxx is easily seen to be 2. fyy is easily seen to be minus 2. And fxy, which is equal to fyx, is 0 as well. There's no simple geometric argument for this. So that's why I'm offering it without proof. Yeah. So what is d in this case? D, which is fxx, fyy minus this squared, is easily seen to be minus 4. So d is negative. So f has a saddle point here at the origin. Let's graph this. Let's graph this function to understand what the graph looks like, and this will explain the word saddle point. What does the graph look like? We are graphing z equals x squared minus y squared. Right, so graph it in the xz plane when y is 0. What happens when y is 0? Well, you know what that looks like. It's just this parabola in the xz plane. And now if you fix a value of x, if x is c, then z is c squared minus y squared. So this is going to be, right, I mean, this is just a constant here. So it's a parabola coming down. A parabola which starts on these values of x, on this graph, and it's coming down. So you see at the origin, well, I mean, very, very close to the origin, this looks like a saddle. A saddle, a horse saddle. And thus the name saddle point. In one direction, the function is increasing, but in another direction, it's decreasing. How are we doing here? So let's take a few examples from the book. Well, it is a good question, right? But I mean, I don't have a good geometric interpretation to offer. We'll go until 1. In fact, you know, I mean, it was going to be short class today because I did not want to discuss the next topic. So we're just going to discuss second derivative test and a few simple applications. Let's do a few questions from the book. We're asked to find local max, min, and saddle points. All right, so you know what you're looking for. We're looking for with regards to the graph, we found, first of all, we are classifying the only point of interest is the origin, because that was the only point where the gradient was 0. And according to this, we saw that d was -4, so less than 0, so we had a saddle point. And if you look at the graph, what I'm suggesting is the graph looks like a saddle, exactly like a saddle at the origin. So that's why we use the name saddle point, right? In one direction, the function is increasing, but in another direction, the function is decreasing. Consider this. Let's look at the partial derivatives. You can just read it off, right? And these exist for all values of x. So the critical points are where both of these are 0. All right, I mean, you've got two equations, two unknowns. You can solve however you wish, matrices or otherwise. From this one, we see that y is 2 plus 2x. If you plug that into here, what do we have? X minus 2 minus 4 minus 4x. So this is minus 3x is equal to 6. X is minus 2. And if x is minus 2, y is minus 2. So we have just the one critical point, minus 2, minus 2. Continue. fxx is minus 2. fxy is 1. And fyy is minus 2 as well. So d, which is fxx, fyy minus fxy squared, is what? In this case, this is 4 minus 1 is 3. So that's bigger than 0. So now it'll depend on the second derivative of f with respect to x. fxx, we have it here. This is less than 0. So local max at, what was it? -2, -2. Let's try a few more. It could have been FYY. Gabriel, you're absolutely right. They are not always the same. No. So you could have done a test based on FYY as well. All right, let's consider this. The local max, no, local max is not, local max is at the point we found, not at fxx, fyy. It's purely coincidental here. Well, first of all, you have to calculate both anyways. And secondly, nobody uses a test based on FYY. So let's not make up our own test here. This is the second derivative test that everybody's familiar with. So let's go with that. Here we go. Did we do FYY without writing? I'm not sure what you mean there. I think it's easy to work out FYY. If you differentiate with respect to x, what do we get? 3x squared plus 3y. If you differentiate with respect to y, 3y squared plus 3x. Again, what if we have multiple critical points? Which happens, absolutely. Right? I mean, you should expect that. In very much the same way as you had multiple critical points in Cal 1. Then you have to check for all of them. The D will depend on the points themselves. Absolutely. We'll see some examples. So again, fxx, fyy both exist. So critical points are where these are equal to 0. So you see the issue here, right? I mean, the issue is really solving for the critical points. These get complicated. Essentially, you have two equations, two unknowns. So whatever you want to do, here's what I'm going to suggest. Let's multiply this equation by x, and let's multiply this equation by y. See what happens. And if we do that, we get 3x cubed plus 3xy is equal to 0. And the other one, 3y cubed plus 3xy is equal to 0. So if you subtract the two, we get 3x cubed minus 3y cubed is equal to 0. They are not, of course, Marie. You know they're not. I'm sure you've taken the derivative of f. I'm sure you've done lots of examples with partial derivatives, and you know they're not always the same. Here they're the same because if you switch x and y, you get the same function. But as soon as it's not, right, if your function is x sine y, then df dx and df dy are completely different. Right, we have this, and if you factor out the 3, you're left with the difference of cubes, which you know factors as x minus y, and x squared, I want to say plus xy plus y squared. Is that even right? This is x cubed minus x squared y plus x squared y, looking good, minus x y squared plus xy squared, looks good. Looks very good. And as usual, you've got a product equal to 0, so one of the factors has to be 0. Either x minus y is equal to 0, or this is equal to 0. And when is that equal to 0? Well, it's a quadratic, so you can use a quadratic formula. Negative b plus or minus square root of b squared minus 4ac all over 2a. And the only time this is not complex is if y is 0, which would mean x is equal to 0, which is contained in here anyways. So there it is. X has to be equal to y, and in that case, we have 3x squared plus 3x is equal to 0. If we factor out of 3x, we get a plus 1, and so x is equal to 0 or minus 1. So we have the two critical points, 0, 0, minus 1, minus 1. Can we write y equals negative x squared? Yeah. Whatever you want to do to solve, it's fine. Right? I mean, it doesn't have to be this way. There are several ways. Well, I mean, because we're solving for x. And here, x, this is a quadratic in x. So you can use the quadratic formula, right? For any value of y, if you fix a y, we're asking the question for what value of x is this equal to 0. So there it is. We have two critical points in this case. Oh, I should have kept that. This was fx and this was fy. Let's look at fxx. If you differentiate this with respect to x, we get 6x. If you differentiate this with respect to y, we get a 3. And if you differentiate this with respect to y, we get a 6y. So you see that now, as is the case in general, D really depends on which point you're looking at. So D at the point 0, 0, which is fxx, fyy minus. So when x is 0, this is 0. So D is -9. And what does it mean when D is negative? Where did the 3x squared plus 3x come from? We had I just rubbed it off now, but fx was 3x squared plus 3y, right? And that was equal to 0. And now we just said x and y are the same. So I'm replacing y with x to get that. Exactly that. So you see that we have a saddle point at the origin. And if you look at D at the point -1, -1, which is what? -6 times -6, which is 36, -9. Well, whatever that is, right? 27. But the important thing is that it's bigger than 0. So now this is going to be determined by what fxx is at that point, and that is, of course, -6, which is less than 0. So we have wasn't fx y Philip, I'm not sure. I think you're referring to the previous question, Philip. So D is bigger than 0, fxx is less than 0, so local max at, not there, at -1, -1. This was again in the previous question. Then fxy is 3. Yeah, exactly that. Everybody with us? Questions? Do we want to do one more, or have we had enough? Shall we move on, or one more? You tell me. Simon, think about the second derivative test in Cal 1, right? You needed the second derivative to be less than 0 to get a local max. Let's do one more. for the quadratic part, you wouldn't get a real answer unless y was 0. But if y is 0, then x is 0. And that solution was part of the x equals y business anyways. So it could be disregarded. Let's look at the partial derivatives. Here you've got a product when you differentiate with respect to x. So product rule applies. 2x e to the minus x minus x squared plus y squared e to the minus x. And derivative with respect to y, 2y e to the minus x. Again, does something interesting happen when we start considering the complex plane? Very much so. Very, very, very much so. The study of complex variables is very rich and demanding, and sometimes even counterintuitive. A lot of stuff happens there. We will not touch that. It's my understanding that some of you have to do a course in complex variables, so you'll see all that beautiful business there. Oh well, no, there is a complex variables for engineering students, or have they removed that? You tell me. There used to be one. I don't remember the course number. It used to be taught by the mathematics department. It might have, it was called complex variables. So here, partial derivatives, right? First of all, these exist everywhere. So the critical points are going to be, it's not 264. So critical points are going to be where these are equal to 0. Let's look at this last one here. 2 is not equal to 0. The exponential is never equal to 0. So this implies that y has to be 0. And if you plug that into this one, if you plug y equal to 0 into this one, what do we get? We get 2x e to the minus x minus x squared e to the minus x is equal to 0, right? I'm plugging in y equal to 0 into this to get that. Let me factor out an x e to the minus x, leaving me with 2 minus x. So there we have it. We have a product equal to 0. So at least one of the factors has to be 0. So either x is 0, the exponential is never 0, and if this is 0, then x has to be 2. So we have 2 critical points, 0, 0, and 0, 2, and 2, 0. How is y equal to 0 from this one here? You have this is equal to 0. The exponential is never 0. 2 is never 0. So y has to be 0. All right. So let's see what happens. What is f(x)(x)? The derivative of this with respect to x? Well, there's still a lot of work to be done there. It's two product rules, right? So 2e to the minus x minus 2x e to the minus x minus 2x e to the minus x plus x squared plus y squared e to the minus x. The derivative of this with respect to y, or the derivative of this with respect to x, is going to be the same, right? By Clairaut's theorem, that is minus 2y e to the minus x. And then the derivative fyy, 2e to the minus x. Everybody should be doing honors. So what is d at the origin when x is 0 and y is 0, everything is 0 here except this. So f(x)(x) is 2, fyy is also 2, and there it is. Midterm should be done by the weekend. I'm the only grader who hasn't finished marking. So by the weekend, I'll be finished. So there's the d, that is bigger than 0. So as you know, the classification will depend on f(x)(x), which is 2 in this case, which is also bigger than 0. So local min at the origin. Well, that's the thing, right? I mean, honors really prepares you well for graduate school. I mean, I can't talk about the other departments and other faculties, but I did honors math, and everybody should do honors. And let's calculate at 2, 0. So y is 0 there, x is 2. So if x is 2, what do we have here? If x is 2, we're going to have a minus 4 plus 2, so that's minus 2. And then here you have a 4 minus 4, so you're left with a minus 2 e to the minus 2. That's what I claim is f(x)(x). fyy is 2e to the minus 2. And this business is going to be 0 again. So regardless of what that is, you know that it is negative. And so you have a saddle point. How are we doing here? All right, so, I mean, we have local max and min, and it's all good. But now if you think back to Cal 1, we actually had the notion of absolute max and min. Right? And in fact, we had a nice theorem that said that if f is continuous on a closed and bounded interval AB, then f attains an absolute max and an absolute min. And you know where these were attained. These could occur either at critical points or at the endpoints. Only one variable here. This is a Cal 1 theorem. But you're right. No need to retract. You're right, and we're going to extend that in just a moment. Right? These can occur at critical points or the endpoints. Endpoints of the interval. Exactly that one. The second derivative test is just evaluating the determinant. Not of the Jacobian, because Jacobian is first order, right? So it's like a second order, and somebody had called it correctly before. It's called the Hessian Matrix. And that's how you can actually extend the second derivative test to higher dimensions via this Hessian matrix. But we've moved on from there. Perhaps Professor Humphreys will discuss it. We will not. A continuous function on a closed and bounded interval attains an absolute max and an absolute min. And again, right, this is a result from Cal 1. Where do these occur? They occur at critical points or at the endpoints. We have an extension of this theorem to higher dimensions, and it extends exactly as you would expect. A continuous function on a closed and bounded domain attains an absolute max and an absolute min. And where can these occur? In exactly the generalization of the above theorem. at critical points, or, and well, I mean, in this theorem, it was endpoints, right? Because it was the end of your domain, continuous, a continuous function. So critical points or the end of your domain, or the boundary of the domain. And now, I mean, the obvious question arises, what is the boundary? Well, but the boundary is exactly what you think it is. Right? The boundary is what you cross to go out of your domain or to go into the domain. Right? If this is your domain, then the boundary is this. Is this. It's what you cross to get out or to go back in. It's like a border. It's a border. Let's take some examples. In these questions, we are asked to find the absolute max and min. What section of the book? I don't know. But it's page 1027. I mean, what did I say? 1017. Thank you, Malloy. When you say closed and bounded, bounded just means that it has no side going off to infinity. Exactly. You can say bounded if you can draw a circle around the domain. A circle with finite radius. What's the difference between the two theorems? This is just an extension of that one. This is in the one variable case, right? The theorem you remember from Cal 1. Now it's in the two variable case. Vertices. So triangular region with vertices 0, 0, 0, 2, and 4, 0. Let's take a moment to draw this region to understand what's happening. So the origin, x, y, so 0, 2. And 4, 0. So there it is. This is our closed and bounded domain. We have a polynomial in x and y. Hovering above, right, in the third dimension, in the z. So it's hovering above. And we're looking for the absolute max and the absolute min. No, drawing is important. Drawing is very important here. It's just a rough graph. And it's not even this function, right? We're not drawing this. We're just drawing the domain. And drawing the domain is very important here. It's very important because we're looking for the absolute max and min, and you know where these can occur. They can occur at critical points or at the endpoints. Oh, well, critical points, or in this case, on the boundary. Right? And the boundary is the collection of these three line segments. So it's difficult to visualize that if you haven't drawn the region. And you know, I mean, if your drawing skills aren't that good, practice, practice, practice. You get better with practice. All right. So first, let's look for critical points that are inside the domain. What is the derivative with respect to x? Well, you know what it is. 1 minus y. Derivative with respect to y? 1 minus x. Again, these exist everywhere, so critical points are going to be where this is equal to 0. And immediately you see that you have a critical point of 1, 1. It's not immediately clear that 1, 1 is inside the domain. So we have to verify. And we're going to verify by working out what this line is. You know what that line is. Minus 1/2 x plus 2, is that right? Does everybody have that? Is that right? Thank you. So when x is 1, this point right here on that line is 3/2, which is bigger than the point 1, well, which is bigger than 1. So the critical point 1, 1 is in your domain. A very important observation. And as the theorem, the theorem I've just erased here, suggested, the absolute max and min can occur at critical points or on the boundary. So the boundary here is made up of 3 line segments. Let's call them C1, C2, and C3. What are these line segments? How can you describe those line segments? C1 is the line segment from 0, 0 to 4, 0. Well, I mean, it's a line in 2 dimensions, so let's describe it. Well, we don't need to find the directional derivative here. What I'm saying is we're going to describe C1, right? Because the maximum and minimum may occur on C1. But C1 is the straight line going from 0, 0 to 4, 0. So, I mean, it has direction vector 1, 0. And it goes through the origin. So it goes through the origin 0, 0 plus t times the direction vector 0, 1. So now you do 3 single variable optimizations. Very nice. Very nice observation. That's exactly what you do. And how did we find, it's not 1/2, right? There's a minus here. It's minus 1/2 x plus 2. And this is the equation of C1 in 2D, where t goes from 0 to 4. This is a 2D graph. We do not need to graph the region. Well, I mean, maybe you do. What I'm saying is you don't need to graph this function hovering above, but you do need to understand what your domain is. Exactly as Louis suggested. So on C1, your function evaluated at t0, when x is t and y is 0, you just have the function t. So now you know how to maximize that and minimize, right? You find the critical points of this function of one variable, and critical points, and the max and min can occur at critical points or at the endpoints. Here there are no critical points, so the max has to occur at one of these points and the min at the other. This is the max, this is the min. On C1. Repeat. Repeat. On C2, C2 has this line as equation. So let's describe it in parametric form. X is t, y is minus 1/2 t plus 2. And we want to describe just this line segment. So t is going to go from 0, when t is 0, you're at this point, all the way to t equals 4. When t is 4, you're at the point 4, 0, exactly there. So now let's look at our function on that line. So when x is t, y is this. Let me just rewrite my function here so I don't forget. What is that? T minus 1/2 t. That's 1/2 t plus 2 plus 1/2 t squared minus 2t. Or, if you prefer, minus 3 over 2t plus 2 plus 1/2 t squared. Let's take the derivative of this. That is minus 3 over 2 plus t critical points. Why is it t plus minus 1/2? Well, this is my function. So I'm replacing x with t and y with this. Derivative is this, and critical points. T is 3/2, which is in the interval. So you know max and min of this function can occur at critical points or at the endpoints. So at the endpoints, this is f of when x is, when t is 0 and y is 2, we get 2. And at 4, 0, it's going to be the same, right? We already worked that out. But now we have the extra point, 3/2. And when t is 3/2, this is minus 3/4. So 5/4, is that right? Is that correct? I think so. Or just plug in 3/2 into this. Maybe that'll be easier. That's minus 9/4 plus 2 plus 9/8. So that's minus 9/8. 16 minus 9 is 7/8. 7/8 sounds right. Finally, on C3, parametric equation of your line, x is always 0, y is t, where t goes from 0 to 2. Let's recall that we had a critical point of 1, 1. So your function on that line segment, when x is 0 and y is t, we just get a t. And it was very similar to this one. So the derivative is just 1, no critical points here. And the maximum is going to occur at one of these values, and the minimum is going to occur at the other one, and of course it is easily seen to be min and max. Either way, you can plug 3 and 5/4 into this, which is going to be equivalent to plugging in 3/2 into this. Convince yourselves? So now, finally, let's put everything together by looking at the values, all these values, along with the function at the critical point. F of 1, 1 which turns out to be 1. So what is the min and max on C2? C2 was this one. We had critical points and endpoints. It's easy to see that this is the minimum and this is the maximum. No need to point that out because we're looking for the absolute max and min in the end. So now you have to look at all of these values. Whichever one is smallest is the absolute max. Whichever one is largest is the absolute min. And I think it's clear that the absolute max something is wrong, isn't it? What went wrong? Does anybody see a mistake somewhere? No? Maybe there's no mistake. All right, fair enough. So, conclusion? Smallest value among these? Minimum of 0 occurring at the origin. Maximum of 4 occurring at 4, 0. So there it is. This is the minimum. This is the maximum. No, I was just I don't know. For some reason, I thought there was a mistake, but there's no mistake. Why are we looking for the max and min on domain when we want the absolute max and min on the range? Well, we're looking for where the maximum and minimum occur. So here I'm suggesting that the minimum is going to be 0 and the maximum is going to be 4. And that's where they occur. What f of 0, 2? Well, f of 0, 2 was 2, right? And it was just 2. So it's not a max nor a min. Exactly that. So there it is. That gives you the flavor of what needs to be done. You need to describe, right? So first of all, what are we doing? We're finding a max and min of a function on a closed and bounded domain. You look for critical points, right? Where can the max and min occur? They can occur at critical points or on the boundary. So you need to describe your boundary. Exactly that. In this case, we described it as 3 line segments. And we maximize and minimize the function on each of these segments. We don't need to talk about local max or min. Here the question was absolute. What happened with the C3? The minimum occurred at the origin. There it is. One could be a saddle point, right? We'd have to look at the second derivatives. What happened to the point 1, 1? Well, at the point 1, 1, the function is 1. So it's neither a min nor a max. Well, it's neither the absolute min nor the absolute max. Might be a local min, might be a local max. Somebody's suggesting there was a saddle point. You'd have to apply the second derivative test to see what happens there. Well, here, we're just maximizing and minimizing functions. Why did we do d by dt? Because we had a function of one variable. Your line segment is a one-dimensional object. So when you look at the function on the line segment, it's a function of one variable only. If it was a local max or min, there would be another critical point. I don't know that to be true. Exactly that, Gabriella. We found the max and min in a one variable case, the same as Cal 1. Exactly that. Work this out. We'll do maybe one more next time, and then we'll see it another approach to treating the boundary. Thank you all for coming. Yeah, exactly. We find the derivative. We use the derivative to find the max and min in exactly the way you did in Cal 1, because now it's a function of one variable. All right. Thank you all for coming, folks. I will see you on Thursday.